Hi, and welcome to the 33rd day of Just Start Programming, the Rust programming language. Today we are still on the topic of asynchronous programming, features in sequence, and then we will look into the traits for async. So if you're with me watching this video, join me once again live in one take, no shortcuts and no secrets. So let's just start programming. Okay, so here we are. Streams, features in sequence. I think this is the one we did yesterday. Let me check in our Visual Studio Code. Get message. Let's get message, respond task, get intervals. Intervals. Okay, so I think we stopped somewhere here. So let's backtrack a little bit. So this is on the topic of merging the streams. And then over here we have composing streams. Okay, let's start from here. So it says there are many concepts naturally represented as streams. Items becoming available in queue. Chunks of data being pulled incrementally from the file system when the full data is too large for the computer's memory, or data arriving over network over time. Because streams are features, we can use them with any kind of feature, combine them in interesting ways. So in this example, so to avoid triggering too many network calls, set timeouts on sequence of long-running operations. Throttle user interface events to avoid doing needless work. Let's start by building a little stream of message as stand-in. For stream of data we might see from WebSocket or another real-time communication protocol. Here we still have the runtime here, the scope of async, and here we are calling the method get message. Implements stream, messages, while let some messages next. So next is a function from stream. So just like iterator, you can call next. And here get messages. So there's a channel messages array for message in messages. So there's a transmit, so it will send a message, a string. So we have a little bit of error handling here. Then receiver stream. Here, new receiver. Okay, so how does this work? There's a function called get message that returns this. then for its implementation, we create an async channel loop over the first 10 letters of the English alphabet. So that is this part. We also use a new type, receiver stream, which converts our X receiver from the RPL channel into a stream with next method. Back in main, we use a while let loop to print all the messages from the stream. When we run this code, we get exactly the results we would expect. So although it's a stream, it will send these characters. And these characters are the message. And once it is received, it will print. Yeah, so that's how it works. Again, we could do this with a regular receiver API or even a regular iterator API, though let's add a feature that requires streams. Adding a timeout that applies to every item in the stream and delay on the items we emit. So there's a timeout here. So get messages is actually a stream. So a stream will have a timeout function. So if it times out within 200 milliseconds, message next. So sum, if it's okay, then it will print the message. If there's an error, then problem, and then the reason. Yeah, but I think while trying this out the other day, here. However, because there are no delays between messages, this timeout does not change the behavior of the program. It will never time out. Okay, but over here, there's a slight change. So messages into iterator enumerate. So it will return a tuple that time sleep if modulo 2 100. Time sleep is 100 if it's divisible by 2. Else it's 300. Then sleep duration from millis. So depending whether the index is divisible by 2. So there's a little bit of variation being introduced here. Transmit, send message and wrap. Okay, then receiver stream is here. Okay, so we're applying 100 millisecond delay to even index items and 300 millisecond delay to odd index. So most likely the 300 millisecond delay will time out because the timeout is 200 milliseconds. So as you can see from here, this is index 1, this is index 2, so divisible by, no, this is 0, this is 1. So this one will be 300 milliseconds and it will display an error like this, mainly because of the time. Okay, then we moved on to merging streams. How do we merge streams? Okay, create another stream which will emit an item every millisecond if we let it run directly. For simplicity, we can use the sleep function to send a message on a delay and combine it with the same approach using get messages, creating a string from channel. Okay, so here there's a sleep of 1 millis await, and there's a counter, a send a count. We start by defining a count in the task. You could define it outside the task too, but it's clearer to limit the scope of any given variable. Copy that here. Yeah, so we're now in this function. Get intervals. Okay, so it's never used. Not yet used. Okay, then we create an infinite loop. Where's the infinite loop? Yeah, the infinite loop is over here. Each iteration of the loop asynchronously sleeps for 1 millisecond. Increments the count, and sends it over the channel. Because this is all wrapped in a task created by spawn task, all of it, including the infinite loop, will get cleaned up along with the runtime. This kind of infinite loop, which ends only when the whole runtime gets torn down, is fairly common in async Rust. Many programs need to keep running indefinitely with async. This doesn't block anything else. As long as there is at least one await point each iteration through the loop. Now back in our main function's async block, we can attempt to merge the messages in interval streams as shown. So in main, you have messages, get messages, intervals, get intervals, and merge. Let me copy this one. Get messages. No, not yet. So I'm gonna comment this out. And yeah, we know that it will not compile, but let's just copy it. Intervals. So there's an error here. Required by a bound introduced by this call. Required by a bound in merge. Okay, we start by calling get intervals. Where is it? Okay, we start by calling get intervals, then we merge the messages merge, and interval streams with the merge method here, which combines multiple streams into one stream that produces items from any of the source streams as soon as the items are available, without imposing any particular ordering. Finally, we loop over that combined stream instead of over messages. At this point, neither messages nor intervals needs to be pinned or mutable, because both will be combined into the single merge stream. However, this call to merge doesn't compile. Yeah. Neither does the next call in the while let loop. But we'll come back to that. This is because the two streams have different types. The messages stream has a type timeout, IMPL stream, item stream, where timeout is the type that implements stream for a timeout call. The interval stream has type IMPL stream.
item U32. To merge these two streams, you need to transform one of them to match the other. This is the requirement. We'll rework the interval stream because messages is already in the basic format we want and has to handle timeout errors. Okay, but before that, let's take a look over here. So it says there are two different, cannot merge because you have two different types. Intervals, you can see implement stream item U32. But messages is a timeout. And then inside timeout, you have implement stream item. We don't know. So let's follow this approach. What did it do? Intervals, get intervals. Then there's a map count. Okay, so you can see here there's a timeout. It should be similar to this one. So now both of them will return timeout. Okay, let's copy this part. Comment this out and put it here. Okay, so now the compilation is gone. Now you can see this part is a timeout, this one is also a timeout. Then you can merge. Self timeout. Oh, this one has a no. You're referring to self. Okay. Okay, so first we can use the map helper method to transform intervals into a string. Second, we need to match the timeout from messages because we don't actually want a timeout for intervals, though we can just create a timeout which is longer than the other durations we are using. Here we create a 10-second timeout. Okay, so actually it's not needed, but it's added here. Finally, we need to make stream mutable. There's no mut here. Okay, so that the while-let loops next calls can iterate through them. Okay, and pin it so that it's safe to do so. That gets us almost to where we need to be. Everything types checks. If you run this though, there will be two problems. Okay, stream is mutable here, and then you have a pin. I think I forgot to copy this. Merged. Okay. Not stream. First, it will never stop. You'll need to stop it with Control C. Second, the messages from the English alphabet will be buried in the midst all interval counters. Okay, that's interesting. Let's try to run this one. Did it run? Did it do anything? wrong. We're supposed to see something like this. Run this here, async. Let mod stream. Did I miss anything? Maybe let me just copy this once again. Nothing happened. Why? Don't know why nothing happened. Get message. Do this time to sleep. Wrap. Sync move. Sync move. Spawn task. TRPL channel. Spawn task. Sync move. Okay, so we have this. Get intervals. It did not display anything similar to this at all. Okay, so let's try this one instead and see. Delete this one. What happened here? TPRL run async. run async, get message, async move, stream. We have this. The output is not exactly the same. Let me copy that one and comment out this part. And then paste the new one. Let's run it again and see. Executing task cargo run. You're not seeing the printout. Why? In merged. Should be seeing this part. Function main. Okay, get messages. I don't understand why it's not running. What did we miss? Okay, so originally it was this. Get message. Okay, can we come back to this one? Main. Where's the runtime? Did you miss out the runtime? Okay, run is here. Okay, that one is running. Next would be no change from here. Okay, this one was displayed from get intervals, and this one will compile, change it to this. So why not we change it to this? This one is not running for I don't know what reason. I think there's something wrong with this one. Time out. Time out 200 milliseconds. Can I put just guessing? Maybe let's change this a little bit. Millis. So instead of 10, let me put it 300. Finished. Nothing was there. Nothing seems to be working from this example, and I don't know why. Okay, so instead of making this work, might as well move on to the next topic. Maybe I'll take a look what's really wrong here after we have finished the book. Okay, so anyway, sorry for that. Let's move on to how future, stream, and other key traits Rust uses to make async work. Okay, so let's read closer look at the traits for async. Throughout the chapter, we have used feature, pin, unpin, stream, and stream ext stream extension traits in various ways. So far, though, we have avoided getting too far into the details of how they work or how they fit together, which is fine most of the time for your day-to-day Rust work. Sometimes, though, you'll encounter situations where you'll need to understand a few more of these details In this section, we'll dig in just enough to help in those scenarios, still leaving the really deep dive for other documentation. The feature trait. Let's start by taking a closer look at how the feature trait works. Here's how Rust defines it. As context, all feature, public trait feature, type, output. And then you have a poll. Okay, that trait definition includes a bunch of new types and also some syntax we haven't seen before. So let's walk through the definition piece by piece. First, features associated type output says what the feature resolves to. This is analogous to item associated type for the iterator trait. Second, feature also has the poll method, which takes a special pin reference for itself, parameter, and mutable reference to a context, and returns poll self output. Okay, we'll talk more about pin and context in a moment. For now, let's focus on what the method returns, the poll type. So the poll type is an enum, ready and pending. This poll type is similar to an option. It has one variant that has a value ready and one which does not, pending. Okay, so you have ready and pending. Poll means something quite different from option. Though the pending variant indicates the feature still has work to do, so the caller will need to check again later. The ready variant indicates that the feature has finished its work and the t value is available. Finished and t value is available. Note, with most features, the caller should not call poll again after the feature has returned ready. Many features will panic if polled again after becoming ready. Features that are safe to poll again will say so explicitly in their documentation. This is similar to how iterator next behaves. When you see the code that uses await, Rust compiles it under the hood to code that calls poll. If you look back in 17-4, we printed out the page title for a single URL once it resolved. Rust compiles it into something kind of, although not exactly like this. Okay, something kind of like this. Okay. What should we do when the feature is still pending? We need some way to try again and again and again until the feature is finally ready. In other words, we need a loop. Okay, so we need a loop. If Rust compiled it to exactly that code, though every await would be blocking, exactly the opposite of what we were going for. Instead, Rust makes sure that the loop can hand off control to something that can pause work on this feature to work on other features, and then check this one again later. As we've seen that something is an async runtime, and this scheduling and coordination work is one of its main jobs. Earlier in the chapter, we described waiting on receive. The receive call returns a feature, and awaiting the feature polls it. We noted that a runtime will pause the feature until it's ready with either some message or none when the channel closes. With our deeper understanding of the feature trait, and specifically feature poll, we can see how that works. The runtime knows the future isn't ready when it returns Paul pending. Conversely, the runtime knows the future is ready and advances it when Paul returns Paul ready. Okay. The exact details of how a runtime does that are beyond the scope of this book, but the key is to see the basic mechanics of futures. A runtime calls each future it is responsible for, putting the future back to sleep when it is not yet ready. The pin and unpin traits. When we introduced the idea of pinning in listing 17-16, we ran into a very gnarly error message. Here's the relevant part of it again. Join all features await, the trait unpin is not implemented. So consider using the pin macro. Okay, using the pin macro. This error message tells us not only that we need to pin the values, but also why pinning is required. The TRPL join all function returns a struct called join all. That struct is generic over a type F, which is constrained to implement the future trait. Directly awaiting a future with await pins the future implicitly. That's why we don't need to use pin macro. Okay. Directly awaiting a future with await pins the future implicitly. Everywhere we want to await future, so it's a future. Await pins the future implicitly. However, we're not directly awaiting a future here. Instead, we construct a new future, join all, by passing a collection of futures to the join all function. The signature for join all requires that the types of the items in the collection all implement the future trait, and box T implements future only if T it wraps is a future that implements the unpin trait. That's a lot to absorb, yes, definitely. To really understand it, let's dive a little further into how the future trait actually works, in particular around pinning. Okay, look again at the definition of the future trait. Okay, so we have future output Paul. The CX parameter and its context type are the key to how runtime actually knows when to check any given feature while still being lazy. Again, the details of how that works are beyond the scope of this chapter, and you generally only need to think about this when writing a custom feature implementation. We'll focus instead on the type of self, as this is the first time we've seen method where self has a type annotation. A type annotation for self works like type annotations for other function parameters, but with two key differences. It tells Rust what type self must be for the method to be called. It can't be just any type. It's restricted to the type on which the method is implemented. A reference or a smart pointer to the type, or a pin wrapping the reference to the type. Pin wrapping a reference to the type. We'll see more on this syntax in chapter 18. Okay. For now, it's enough to know that we want to call a feature to check whether it's pending or ready. We need a pin wrapped mutable reference to the type. Pin is a wrapper for pointer-like types such as ampersand, mod, box, and RC. Technically, pin works with types that implements the deref or deref mod traits. But this is effectively equivalent to working only with pointers. Pin is not a pointer itself and doesn't have any behavior of its own like RC and ARC do with reference counting. It's purely a tool the compiler can use to enforce constraints on pointer usage. Recalling that await is implemented in terms of calls to Paul starts to explain the error message we saw earlier, but that was in terms of unpin, not pin. So how exactly does pin relate to unpin? And why does future need self to be in a pin type called Paul, to call Paul? Pin. Okay, to call Paul. Okay. Remember from earlier in this chapter a series of await points in the future get compiled into a state machine, and the compiler makes sure that the state machine follows all of Rust's normal rules around safety, including borrowing and ownership. To make that work, Rust looks at what data is needed between one await point and either the next await point or the end of the async block. He then creates a corresponding variant in the compiled state machine. Each variant gets the access it needs to the data that will be used in that section of the source code, whether by taking ownership of that data or by getting a mutable or immutable reference to it. So far, so good. If we get anything wrong about the ownership or references in a given async doc, the borrow checker will tell us. When we want to move around the feature that corresponds to that block, like moving it into a vec, to pass to join all, things get trickier. When we move a feature, whether by pushing it into a data structure or data structure to use as an iterator with join all, or by returning it from a function, that actually means moving the state machine Rust creates for us. And unlike most other types in Rust, the features Rust creates for async blocks can end up with references to themselves in the fields of any given variant, as shown in the simplified illustration, figure 17-4. Self-referential data type. Okay. By default, though, any object that has a reference to itself is unsafe to move. Okay, so feature 1, feature 2. Because references always point to the actual memory address of whatever they refer to. If you move the data structure itself, those internal references will be left pointing to the old location. However, that memory location is now invalid. For one thing, its value will not be updated when you make changes to the data structure. For another, more important thing, the computer is now free to reuse that memory for other purposes. It could end up reading completely unrelated data later. Theoretically, the Rust compiler could try to update every reference to an object whenever it gets moved. But that could add a lot of performance overhead, especially if a whole web of references needs updating. The Rust compiler could try to update every reference to an object whenever it gets moved. But that could add a lot of performance overhead, especially if a whole web of references needs updating. If we could instead make sure that the data structures in question doesn't move in memory, we wouldn't have to update any references. This is exactly what Rust borrow checker requires. In safe code, it prevents you from moving any item with an active reference to it. This is very important. Okay, pin builds on that to give us exact guarantee we need. Whenever we pin a value by wrapping a pointer to that value in pin, it can no longer move. Yeah, so I think that's where they got the name pin it here, so it will never move. Thus, if you have pin box sum type, you actually pin the sum type value, not the box. Okay, so assuming B1 is the box, pin sum type is the future. Okay. In fact, the box pointer can still move freely. Remember, we care about making sure the data ultimately being referenced stays in place. If a pointer moves around but the data it points to is in the same place as in figure 17-7, this one, there's no potential problem. As an independent exercise, look at the docs for the types as well as the std_pin module and try to work out how you do this with pin wrapping a box. The key is that self-referential type itself cannot move because it is still pinned. Moving a box which points to a self-referential future type. So B1 moves to B2, pinning this. B2 points to the future. However, most types are perfectly safe to move around, even if they happen to be behind a pin wrapper. We only need to think about pinning when items have internal references. Primitive values such as numbers and booleans are safe because they obviously don't have any internal references. Neither do most types you normally work with in Rust. You can move around a vec, for example, without worrying. Given only what we've seen so far, if you have a pin vec string, you would have to do everything via the safe but restrictive APIs provided by pin, even though a vec string is always safe to move. Okay, so vec string is sufficient enough. Safe to move if there are no other references to it. We need a way to tell the compiler that it's fine to move items around in cases like this. And that's where unpin comes into play. Unpin is a marker trait, similar to send and sync traits we saw in chapter 16, and thus has no functionality of its own. Marker traits exist only to tell the compiler it's safe to use the type implementing a given trait in a particular context. Unpin informs the compiler that a given type does not need to upload any guarantees about whether the value in question can be safely moved. Just as with send or sync, the compiler implements unpin automatically for all types, where it can prove it is safe. A special case, again similar to send and sync, is where unpin is not implemented for a type. The notation for this is IMPL exclamation unpin for some type, where some type is the name of a type that does need to uphold those guarantees to be safe whenever a pointer to the type is used in a pin. In other words, there are two things to keep in mind about relationship between pin and unpin. First, unpin is the normal case, and exclamation unpin is the special case. Second, whether a type implements unpin or exclamation unpin only matters when you're using a pin pointer to the type, like pin at mod some type. To make that concrete, think about a string. It has a length and Unicode characters that make it up. We can wrap a string in pin. See figure 17-8. However, string automatically implements unpin, as do most other types in Rust. Okay, string automatically implements unpin. Pinning a string, the dotted line indicates that the string implements the unpin trait and thus is not pinned. As a result, we can do things that would be illegal if string implemented exclamation unpin instead, such as replacing one string with another at the exact same location in memory, figure 17-9. This doesn't violate the pin contract because a string has no internal references that make it unsafe to move around. This is precisely why it implements unpin rather than exclamation unpin. Now we know enough to understand the errors reported for that join all call from back in listing 17-17. We originally tried to move the features produced by async block into vect block dynamic feature. But as we've seen, those features may have internal references, so they don't implement unpin. They need to be pinned. And then we can pass the pin type into vect, confident that the underlying data in the features will not be moved. Pin and unpin are mostly important for building low-level libraries or when you're building a runtime itself, rather than for a day-to-day Rust code. This is what I wanted to do, day-to-day Rust code. No need to go down to lower level libraries. So since we are still starting with Rust, so day-to-day should be enough. When you see these traits in error messages, though, now you'll have a better idea of how to fix your code. Okay. Note this combination of pin and unpin makes it possible to safely implement a whole class of complex types in Rust that would otherwise prove challenging because they are self-referential. Types that require pin show up most commonly in async run Rust today, but every once in a while you might see them in other contexts too. Okay, so advanced Rust, async Rust. The specifics of how pin and unpin work and the rules they are required to uphold are covered extensively in the API documentation for std pin. So if you're interested in learning more, that's a great place to start. If you want to understand how things work under the hood or even more detail, see chapter 2 and 4 of Asynchronous Programming in Rust. Oh, there's another book. There is another book. Wow. Okay, so we'll save that in another series. Okay, let's continue. The stream trait. Now that you have a deeper grasp on future pin and unpin traits. Actually, it's quite complicated. It's something you cannot just simply digest in one day, I would say. We can turn our attention to stream trait. As you learned earlier in the chapter, streams are similar to asynchronous iterators. Unlike iterator and future, stream has no definition in the standard library as of this writing, but there is a very common definition from the futures crate used throughout the ecosystem. Let's review the definitions of iterator and future traits before looking at how a stream trait might merge them together from iterator. We have the idea of a sequence. Its next method provides option self item from future. We have the idea of readiness over time. Its poll method provides poll self output. To represent a sequence of items that become ready over time, we define a stream trait that puts those features together. Okay, so you have a stream trait of type item, poll next. The stream trait defines an associated type called item. For the type of the items produced by the stream, this is similar to the iterator, where there may be 0 to many items, and unlike future, where there is always a single output, even if it's the unit type. Stream also defines a method to get those items. We call it poll next. So similar to iterator. We also have poll next. To make it clear that it polls in the same way, future poll does and produces a sequence of items in the same way iterator next does. Its return type combines poll with option. The outer type is poll, because it has to be checked for readiness, just as future does. The inner type is option, because it needs to signal whether there are more messages, just as an iterator does. Something very similar to this definition will likely end up as part of Rust's standard library. In the meantime, it's part of the toolkit most runtimes, so you can rely on it. And everything we cover next should generally apply. In the example we saw in the section on streaming, though, we didn't use poll next or stream, but instead used next and stream extension. We could work directly in terms of poll next API by handwriting our own stream state machines. Of course, just as we could work with futures directly via their poll method. Using await is much nicer, though the stream extension trait supplies the next method, so we can do just that. Note, the actual definition we used earlier in the chapter looks slightly different than this because it supports version of Rust that did not yet support using async functions in traits. As a result, it looks like this. The next type is a struct that implements future and allows us to name the lifetime of the reference to self with next, so that await can work with this method. The stream extension trait is also the home of all the interesting methods available to use with streams. stream extension is automatically implemented for every type that implements stream. But these traits are defined separately to enable the community to iterate on convenience APIs without affecting the foundational trait. In a version of stream extension used in TRPL trait, the trait not only defines the next method but also supplies a default implementation of next that correctly handles the details of calling stream poll next. This means that even when you need to write your own streaming data type, you only have to implement stream. Then anyone who uses your data type can use stream extension and its methods with it automatically. That's all we're going to cover for the low-level details on these traits. To wrap up, let's consider how future, including streams, tasks, and threads all fit together. Okay, let's take a look at this one. So it's a short read. Maybe we can finish this as we still have some time. Okay, let's continue. Putting it all together, futures, tasks, and threads. As we saw in chapter 16, threads provide one approach to concurrency. We've seen another approach in this chapter using async with futures and streams. If you're wondering when to choose method over the other, the answer is it depends, and in many cases the choice isn't threads. Okay, the choice isn't threads or async, but rather threads and async. So you need both. Okay. Many operating systems have supplied threading-based concurrency models for decades now, and many programming languages support them as a result. However, these models are not without their trade-offs. On many operating systems, they use a fair bit of memory for each thread, and they come with some overhead for starting up and shutting down. Threads are also only an option when your operating system and hardware support them. Unlike mainstream desktop and mobile computers, some embedded systems don't have an OS at all. So they also don't have threads. The async model provides a different and ultimately complementary set of trade-offs. The async model, concurrent operations don't require their own threads. Instead, they can run on tasks as when we use TRPL spawn task to kick off work from synchronous function in the stream section. A task is similar to a thread, but instead of being managed by the operating system, it's managed by library level code, the runtime. In the previous section, we saw that we could build a stream using an async channel, and spawning an async task we could call from synchronous code. It's something that didn't work. So we need to revisit that part. We can do the exact same thing with a thread in listing 17-40. We use TRPL spawn task and TRPL sleep. Okay, so in listing 17-41, we replace those with thread spawn and thread sleep APIs from the standard library, the get intervals function. Thread spawn and thread sleep. So thread sleep is here and thread spawn is here. That was the original one. Spawn task and sleep. Spawn task is Tokyo future, and then this one sleep duration. So it will be replaced by thread spawn and sleep. Okay, using std thread APIs instead of async trpl APIs for the get intervals function. If you run this code, the output is identical to that listing 17-40. And notice how little changes here from the perspective of the calling code. What's more, even though one of our functions spawned an async task on the runtime and the other spawned an OS thread, the resulting streams were unaffected by the differences. Yes. So in the runtime, you have async task, while the other one is OS thread. So the get intervals will be replaced by thread spawn and thread sleep. But here, this is still based on runtime. That's what it was trying to say. So resulting streams were unaffected by the differences. Despite their, sorry, my mouse was jumping again. Despite their similarities, these two approaches behave differently, although we might have a hard time measuring it in this very simple example. We could spawn millions of async tasks on any modern personal computer. If we tried to do that with threads, we would literally run out of memory. We could spawn millions of async tasks on any modern personal computer. If we tried to do that with threads, we would literally run out of memory. Okay, so that's the difference. So async or threads. However, there's a reason these APIs are so similar. Threads act as a boundary for sets of synchronous operations. Concurrency is possible between threads. Task acts as boundary for sets of asynchronous operations. Threads act as a boundary for a set of synchronous operations. Concurrency is possible between threads. Okay. Tasks act as a boundary for sets of asynchronous operations. Concurrency is possible both between and within tasks. Because tasks can switch between features in its body. Finally, features are Rust's most granular unit of concurrency, and each feature may represent a tree of other features. The runtime, specifically its executor, manages tasks and tasks manage features. In that regard, tasks are similar to lightweight, runtime managed threads with added capabilities that come from being managed by a runtime instead of by the operating system. This doesn't mean that async tasks are always better than threads, or vice versa. Concurrency with threads is in some ways simpler programming. Yeah, that's true. Simpler programming model than concurrency with async. Async is really quite complex. That can be a strength or a weakness. Threads are somewhat fire and forget. They have no native equivalent to a future. So they simply run to completion without being interrupted except by the operating system itself. That is, they have no built-in support for intra-task concurrency the way features do. Threads in Rust also have no mechanism for cancellation, a subject we haven't covered explicitly in this chapter, but was implied by the fact that whenever we ended a feature, its state got cleaned up correctly. These limitations also make threads harder to compose than features. Okay, again, this limitation also makes threads harder to compose than features. It's much more difficult, for example, to use threads to build helpers such as timeout, and throttle methods we built earlier in this chapter. The fact that futures are richer data structures means they can be composed together more naturally, as we have seen. Tasks then give us additional control over futures, allowing us to choose where and how to group them. And it turns out that threads and tasks often work very well together because tasks can, at least in some runtimes, be moved around between threads. In fact, under the hood, the runtime we have been using, including spawn blocking and spawn task functions, is multi-threaded by default. Many runtimes use an approach called work stealing to transparently move tasks around between threads based on how the threads are currently being utilized. To improve the system's overall performance, that approach actually requires threads and tasks, and therefore futures. When thinking about which method to use when consider these rules of thumb, consider these rules of thumb. If the work is very parallelizable, such as processing a bunch of data where each part can be processed separately, threads are a better choice. If the work is very concurrent, such as handling messages from a bunch of different sources that may come in different intervals or different rates, async is a better choice. And if you need both parallelism and concurrency, you don't have to choose between threads and async. You can use them together freely, letting each one play the part it's best at. For example, listing 17-42 shows a fairly common example of this kind of mixed real-world Rust code. Okay, so you have thread, TRPL channel, thread spawn. Okay, you have thread spawn, and then here you have transmit, send, and wrap, thread sleep. Okay, so this is threading while this is asynchronous. Async await. We begin by creating async channel, then spawn a thread that takes ownership of the sender side of the channel. Within the thread, we send the numbers 1 through 10, sleeping for a second between each. Finally, we run a feature created with async block passed to TRPL run, just as we have throughout the chapter. In that feature, we await those messages, just as in the other message passing examples we have seen. Await. To return to the scenario, we open the chapter with imagine running a set of video encoding tasks using a dedicated thread because video encoding is compute bound, but notifying the UI that those operations are done with async channel. There are countless examples of these kinds of combinations in real-world use cases. Finally, summary. This isn't the last you'll see concurrency in this book. Chapter 21 will apply this concept in a more realistic situation. Let's see, chapter 21. Final project, building a multi-threaded web server. Okay. Looking forward to that. No matter which of these approaches you choose, Rust gives you the tools you need to write safe, fast concurrent code, whether for high throughput web server or an embedded operating system. Next, we'll talk about idiomatic ways to model problems and structure solutions as your Rust programs get bigger. In addition, we'll discuss how Rust idioms relate to those you might be familiar with from object-oriented programming. Okay, so chapter 17, Fundamentals of Asynchronous Programming, Async, Await, Features, and Stream. It's quite a heavy topic, I would say. So it took us several days to cover chapter 17. Yeah, but that's how it is. Let me move forward. Object-oriented programming, features of Rust. Let's take a quick peek on what lies ahead. So OOP, object-oriented programming, and then more theories, more, more reading materials for better understanding. Okay. Inheritance, polymorphism, okay. Trait objects that allow for values of different types. Implementing an object-oriented design pattern. Okay, so design patterns. Okay, so it's a lengthy topic as well. So it's more like organizing as your code becomes bigger, making it more reusable perhaps. All right, so looking forward to that on the next day. All right, so let's end here. Thank you so much for joining me once again. I hope you learned something, although it's mostly reading through concepts, and unfortunately the example here was not as expected, and I'm not sure where exactly it's broken. Yeah, but let's leave it as it is, and then we move on to object-oriented programming next time. Before I finally end, let me thank my supporters.